It was mentioned to me, as I was just chatting, that so we have kind of these three different paradigms that are all happening at the same time. Well, one is already old story, the magnetic disks, right? And you have this, solid state that, you have new disks that have solid state only or solid state hard disk mix. And, sometimes the sequential versus random access is not as big a difference. And the third one is the cloud storage that, you basically don't really have this. You have some basic guarantees, but often you find, so they tell me, people will start shaking their heads, that the data access is much slower than, if it was on your own disk. But, that's also going to change. But, you have to, you are the generations, you and your class who are going to see all this change happening. And you have to be aware of what that means, right? So that's why we are learning this as a way to learn what this design problem leads to in terms of software design. But if that's no longer a problem, maybe it will change how you use systems. So, okay, so I was saying that, RAID is a values method for various things, for increased speed and increased fault tolerance. So the simplest possible RAID is actually RAID 0. It's RAID 1, but there is actually a RAID 0. So let's start with RAID 0. So you have, suppose instead of single hard disk, you have multiple hard disks in your machine. And they are all like these little cylinders. If it helps, you can think that these are sushi rolls. Okay, so put some salmon roe. All right, so you have multiple sushi rolls, and you want to put data in them. Okay, so if you have 4 disks, what you can do is you have your data pages, and you distribute them to these. So you basically store page 1 on this disk, page 2 on this disk, page 3 on this disk, and page 4 on this disk. So, if you need to read this first 4 pages, you can read one bit from each one in parallel. If you were reading it from a single disk, you would have to read it all at once. So basically, in theory, this could be 4 times faster because you're reading it 4 times, from 4 different disks in parallel. Of course, it's not really 4 times faster if those pages were all on the same track, right? But if it actually saves you 4 seats, then it's actually quite good. Then you continue, then you store page 5 here, page 6 here, page 7 here, page 8 here, and so on. And this is called RAID 0, or sometimes called striping. You are distributing your data to multiple disks. And, in general, you hope that reads are faster because you have multiple disks to read from at the same time. And the writes are faster, right? So, because you're not waiting on one disk to write, but you can write to multiple disks at once. But this has absolutely no redundancy. So basically, if one of them fails, you lose all of your data. Right? I mean, technically, if you were lucky, all your data was in one disk, was not distributed, you will not. But technically, you lose all your data if one disk fails. And in fact, if you have 4 disks, it's much more likely that one will fail than if you had 1 disk. You're increasing your possibility of bad things happening. And this is actually a bad karma class, because a couple of times when I was teaching this and recovery and crashing and so on, my actual hard disk is crashed. So this is a reminder, go back up your data. Okay, so that's RAID 0. It's not super useful. It is faster, but it has no redundancy. RAID 1 is very simple. It's basically called mirroring. You have two disks that have exactly the same data. Now the thing is that since you are copying the same data, you are actually using two disks, but you are unable to store twice as much data, right? You're still storing a single, you're storing as much as you can store in one, whereas in the other one you're storing 4 times more data. So you are really wasting one disk just for redundancy, right? So the idea is that if one of them fails, you can use the other one. So RAID 1 basically means that even if one disk fails, the second disk contains all your data, no loss. So we can say that there is redundancy, no loss if one disk fails. Okay. So reads are technically faster because to read the same data, you can choose whichever one you want. And so reads are faster in general, but writes are slower. Because you actually have to coordinate that it's written to both, and then when it succeeds, then your write is complete. Right? So you have to, if you're going to write something to this disk, you also have to copy it to this one, and then you basically are complete. So this is what I have on my desktop in my office. It comes with like some of the kind of slightly high-end desktops. And I do have hardware RAID, and I had to do nothing to configure it, which is nice. I did configure it, but it was very easy. And the nice thing is that the hardware controller also has its own cache, and it can speed things up. So generally, it is a performance game. Okay, so that's RAID 1. We're going to move on, skip ahead to RAID 4. So in RAID 4, I'm going to do a slightly different thing. I'm going to basically have kind of this extra information. So let's say I have 4 disks. So I have disk 1, disk 2, disk 3, and disk 4. I'm going to stripe my pages exactly as I was doing in RAID 1, RAID 0. So let's say this one stores page 1, this one stores page 2, this one stores page 3, and this one stores page 4. And for a second, let's assume that we know the content. So let's say that this is in binary 1, 0, 1, 0, 1, 0, 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1. Okay? So for each of the disks store information, a stream of this. And then I'm going to compute some checksum, some sort of a summary of this information. So there's different algorithms to do that. The simplest one is called the checksum parity. This is called the parity. So I'm going to have a separate disk, which I'm going to call the parity disk. And for these 4 pages, I'm going to have a single parity that is going to be a combination of this. So what I will do is I will take the bits at the same location. So for example, the first 4. And I'm going to look at if the ones are odd or even. Is there a even ones? Yes. So even ones I'm going to put a 0. And odd ones I'm going to put a 1. So 0, 0, and 1. I'm missing 1. 0, 0. This is a 1. So I have 0, 0, 1, 1. This is 0, this is 0, this is 1. Okay? So what I'm doing is I'm storing basically 5 disks. Okay, let's put the sushi rolls. This is very cruel because you're going to be stuck here actually taking an exam. So this is my data, and this is my parity. Okay. So reads are faster because to read data, you can read it in parallel like rate 0. So reads are faster. But writes are now slower. It's actually worse than all the other ones we have seen, because to write any of the 4 pages, I also have to write to the parity. So the parity is a bottleneck. Every time I write, I have to write to parity. So the parity disk has become a bottleneck. But it's not horrible because you don't really need to, let's say if you're changing disk 3, so now disk 3, let's say, is changed to 0, 1, 0, 1, 0, 1, okay? I don't really need to read other 3 pages. All I need is this data and the old parity, okay? So I know that this was 1, now it's 0, so I need to flip this one. This was 0, now it's 1, now I need to flip this one. This is 0, so I'm going to keep this as such. This is 1, this is 0, so I'm going to keep this like this. So to really write, I don't really need to read others, but I still need to read the parity, right? So it's slower. But it can recover from one crash. So can recover from one disk crash. Okay. So if for some reason I lost one of these disks, I can reconstitute its contents by reading the other disks the same page, right? So I know that, for example, looking at what I have 0, 1, 0, 0. I know that the first bit has to be 1, right? So I know that you have 0, 0, 0, 0, so I know that this has to be 0. So the point is that I can recover what information was there, but to recover it, I have to now read from all the disks at once, right, to constitute something that is in page 1. So while you're recovering means that you actually send an order for a new disk, right? So recovery means you buy more disk to put it in there. Once you put the disk in there, then it actually has to construct what was lost. That's also part of recovery. Then when it is finished, it's ready to be used again as before, okay? So if you have RAID, you always buy a few extra disks in the back end because you don't want to wait for it to be shipped while it is in bad state, and if one more fails, then you are dead. So slower during recovery. Okay. And there's one more version of this, which we call RAID 6, I think, or RAID 5. Not sure, 5 or 6. All we do is we basically shuffle the parity disk. Instead of storing the parity on always disk 5, I'm going to shuffle how I store my parity. So, so basically shuffle parity so that it is not a bottleneck. So for example, you would do something like this. So you have disk 1, disk 2, disk 3, disk 4, and disk 5. So, what we had was you had page 1, page 2, page 3, page 4, and this was parity of 1 to 4. For the next page, instead of storing parity here, I'm going to store parity here. Okay? So what I can do is, or I can store it here, just for a change. So I can store page 5, page 6, page 7, and page 8. But now I store my parity here, parity of 5 to 8. And now I do page 9, page 10, page 11, page 11, page 12, and now my parity is here. Since you shuffle the parity, your writes are a little faster because you are not all trying to write always to the same disk. Depending on which page you are writing, your parity will be in a different one. Yes?
Is there an order to how you switch up and do parity?
No. I mean, it will really depend on what the controller is doing. So the conversation I was having is that if you're implementing something like this, when you use software array, it actually writes this mapping somewhere. And if that part of the disk fails, even though disks are fine otherwise, there's a bad sector that contains this, you lose all your data. This is why one of the software array problems. But yeah, the controller knows. And then there are others which I will not go into, but basically, for example, there is RAID 6, and then, I'm sure there's like RAID 8 and so on. But in RAID 6, you actually have a 2-bit parity. Given, all your data, you compute 2-bit parity using an encoding system like Hamming code. Two-bit parity. That means now you have two parity disks, right? So you have n data disks plus 2 parity disks. You can stripe the parity as before, but the beauty of this one is that now you can recover from 2 failures. If one disk fails, you can recover like we did. Second disk fails, you still can recover the data using the remaining information. The third disk fails, where somebody comes and says, why didn't you buy a new one? Right, by that time. RAID 6 is kind of when you really, really want stable storage. So this is kind of the general idea of RAID, which, coming out of database systems you should know about. It kind of builds on the idea that even though magnetic disks are slow, you can buy a lot of them. And you can implement fast storage. And for big data stores, you almost always will have a RAID, if not on your machine, but obviously for big data storage. Any questions on this? Okay. I know it's boring, but we're going through little things. We're coming to it. All right, so now the fascinating world of hard disks continues. We're going to talk about how the data is actually stored on disk. Okay. And from this point on, we are going to move on to actual indexing. But if you understand what I'm doing now, this will really help what comes next. Okay, so all right, the final thing to remember to learn today, and then before we move on to indexes, is how we actually store tuples on disk, right? So generally speaking, you said that your data is stored on disk, but the reality of it is very complex. So first of all, the physical address of a tuple is very long, right? But generally, you will store multiple tuples on a single disk page, right? So generally, a disk page or a disk block stores many tuples. But sometimes your tuples may have these massive pieces of text, right? Like in the reviews for Yelp, you have big text blocks. It may happen that that text block is so large. For example, the Postgres text data type can store up to like a gigabyte or something. It can be huge. If so, then a tuple can also span multiple disk pages, right? But for most of the smaller things, just imagine that a single table can span multiple tuples can be in a single page. So, given that is the case, it doesn't make sense for each tuple to store the full physical address because there are multiple tuples on the same page. So the physical address can be a huge thing, right? Basically, we said it's the surface and sector and track, and it's a huge piece of work. Instead, you generally, instead of using a physical tuple address for where that tuple is stored on disk, you generally have a logical tuple address. Right? This is like, surface, number, track number, and sector number versus tuple 1, 2, 3, 4, right? And the database maintains what that tuple address is. If your tuple currently on disk, it's this maps to its physical address, then you read it from disk to memory, it's this memory address. So basically, there is a mapping table that tells you where tuple 1 is currently, right? So tuple 1 is currently at that physical address, and that go and read it from disk, or tuple 1 is currently in memory, you're welcome to use it. So basically, there's this mapping address that's maintained by the database, and they keep changing the address. That's called pointer swizzling. If you want to ever learn that word, okay? It swizzles in and out the pointer to where the tuple is stored. Okay, switching around. So, okay. But the most important thing to remember is that tuple has an address. You were with me so far? All right, tuple has an address, which tells me where it is stored. And often it is stored on disk. In the rare event that it was brought into memory by some other transaction, it may actually be in memory that I can be used, but almost always it is on disk. When it's on disk, it's in a disk page. And the disk page basically, is many bytes of data, let's say like 8K. So that means it can store multiple tuples. And generally, the way it's maintained will depend on what database system you use. For example, in Postgres, you have this idea that you have first a header. So this is a disk page here. And generally, it stores the tuples near the end. So you have tuple 1, tuple 2, tuple 3, tuple 4, tuple 5. Okay. Generally in the order that you insert them. And then here you have tuple address information. So, tuple 1 offset, tuple 2 offset. And then in between here, you have free space. This allows you so that, if you insert a new tuple, you can put the data for it here, and then you can put the tuple here so they can both make up without really moving the other data around. So the header itself will contain things like, for example, transaction data. When was the last transaction that changed this data page? This is going to be important when we do transactions. The tuple's address will tell you where different attributes are. Remember, you can define your attribute as integer. Integer is a fixed length. Character string that has a fixed length, but if it's a variable length, you have to tell how long that specific string is. So this will tell you where the different fields are going to have the start and end points. Then you store the data as a basically its string right there. Okay. So given that the data is stored as such, we want to find information that is stored in a table, then we need to basically access the data. So we basically talk about primary access versus secondary access. Okay. So the primary access is just access the data. So access the the data pages that the table is stored in. So if I tell you, find me the, so suppose, here's my query. So I say select, so you have table T that has A and B. And my query for you is select B from T where A is equal to 5. Okay? So what is the algorithm to find the B for A is equal to 5? Just give me a second. Tell me. What do I need to do? So that means do I have to read all of the pages or some of the pages? Well, if there is no specific ordering to the data, right? So if I don't know anything about the data, right, I need to read every single data page that this table is stored in, find all tuples that A is equal to 5, and then return T, right? This is called the primary access. Data is stored where it's stored. Read all the pages that this table is stored in, and find the tuples that satisfy this condition, and then return the D values, right? So basically, read all data pages to answer the query. Now, primary access is great, but it may be that you have 100 pages of data, but only one of those pages really contain your answer. Is there a quicker way to do that? Well, what you can do is you can create an additional structure for querying this, a secondary structure, where you can create an index on a search key. Right? So let's say I create a search key A. Let's say if there's an index on attribute A, then I can use the index to find which tuples have this information. Then I can find the B value for those. So that's basically the idea of an index that is generally a secondary access structure. Generally, but not always. So let's try to think about what an index would look like. Okay, this is the part that when I teach this, often people will have trouble. So I'm doing slowly, and then it gets faster after this. Okay, so your data is stored on pages. So this is T of A and B. So let's say you have page 1 and page 2 for 2 pages for this table. Okay. So let's say that these tables store this kind of information. So one tuple T1 has A of 11, B of A. T2 has A of 15, B of B. Tuple 3 has 1C, and tuple 4 has 4 and D. And this one has tuple 5 8E, tuple 6, 21F, and tuple 7, 25G. Okay? So this is the primary access. If I wanted to answer this query, I would read these 2 pages. I'm doing 2 because 2 is easier. Now I want to create an index on, let's call this index I1 on T of A, okay, which is the first value here. So what I can do is I can look up all the values that are stored and which tuple stored it, the tuple address, and put that information itself on a disk page. So page, I'm going to call X of I1. Now my index is going to store different information because I'm only indexing on A attribute, so I don't care about B attribute. So in this case, I'm going to say, okay, what is the smallest one? 1. So there is tuple 3 that contains 1, tuple 4 that contains 4. Then I have tuple 5 that contains 8. Then I have tuple 1 that contains 11. Maybe I run out of space. I need another page, page Y for I1. Okay, so now I have 11, I have 15 is tuple 2 is 15. Tuple 6 is 21. And tuple 7 is 25. Okay. So in addition to 2 pages for the relation, now I have 2 pages for the index. But it turns out that I can maybe put 4 tuples of the relation in a disk page because it has many attributes. But in the index, maybe I can squeeze more because I have to store fewer information because I don't care about a lot of attributes. So it may turn out I can store more entries in an index. So this is my index. So now if I were to answer the same query, right, which was select B from T where A is equal to 5. Okay? Now what I can do is I can quickly tell you that there is no A is equal to 5, right? We are done. I can search the index. The first page is P of X. Given that there is no A is equal to 5, I know I am done. If it is, let's say, if it is 8, if A is equal to 8, right, I can scan the index. The index will tell me, if I look at P of X, that there's a tuple 5, right? But looking at the index, do I know what the B value is? No. So the index tells me a tuple exists, and it is stored in this T5. The T5 is actually in page 1. Okay? That means I have to go and read page 1, and if I read page 1, this is a horrible index. No, this is page 2. If I read page 2, I know that it is E, then I can return E. Okay? So to get to this, I had to scan the index for A, and I had to find the tuple to read from data pages because of B. Then read the data page for B attribute. It happens that this is what we call a dense index because for every tuple I'm storing an actual entry, right? For every tuple in the relation, I have an information in the index. So this is called a dense index. So dense index, meaning that 1 entry per tuple. Now, if you look very closely, that the B attribute, the second attribute, is actually sorted, right? So my data is actually sorted by this. Suppose I know that the data is actually sorted by B, right? You with me so far? Okay. Now, I don't really need to tell you, I don't really need to store one entry for each tuple. Instead, I can store a slightly different index. So I'm going to use the same table, okay? But I'm going to create a sparse index, I2, for T of B. And that's only possible if T of B, if T is sorted by attribute B. Okay. Now I2 is going to be very different. So for I2, I'm going to say, let's call this P of W. I'm going to store two simple entries. Okay. This one is slightly different. It tells me if the B value is less than 8, then go to page 1. If it is greater than or equal to 8, go to page 2. Right? Because I don't really need to, tell you every single thing. Is value 2 there? Well, go to page 1 and see. I don't care. Right? So, so because this is sparse, I cannot really tell everything. But since I don't have to store as much information, I can put much more information in each page. So now, if I want to find, select A from T where B is equal to 5, B is equal to, let's say, C. It is not A, it is E. I'm sorry, you guys are sleeping. All right, that means I should leave you alone soon. So, where B is equal to C, I know that if C is less than E, then it must be stored in page 1. So if I read page 1, I will find that there is in fact a C, then I will return 1. Okay? So, attribute B, so this is attribute A, this is attribute B. This tells me values less than E are stored in this page, values greater than or equal to E are stored in this page. So if I'm searching for C, then it must be in page 1, if it exists. So go and read data page P1, find the tuple for C. If one exists, then return A. Okay? So sparse indices are possible if the data is stored by sorted order. Right. So with this, I will leave you with one final thought and then give you a little bit of a break before the exam. Okay. So what we will learn next time is basically an index called B tree, which are really the bread and butter of indexing of databases. So B trees are basically mostly secondary indices, but not always. Okay. So the idea of a B tree is that at the leaf level, they are dense indices that store information about where the tuples are stored, right? So this is generally dense index pointing to data tuples. But this is sorted by whatever you are indexing. Since it is sorted, I can now create multi-level index that builds, that indices the upper level. So here I'm going to create sparse indices for lower level of the B tree. Okay. So basically, dense in the bottom, but you can use sparse indices on the top by basically summarizing information more and more. And there are lots of rules about them, but we will do all of that on Monday. But there's one final thing to say, okay? Secondary versus primary, okay? So whenever you say something is a secondary index, that means you have data pages and you have additional index, right? So you basically have data pages stored in no particular order, plus you have an index structure. Your index doesn't have to be a B tree. There are different kinds of indices. We will talk about hashes. We will talk about bitmaps. And if you have time, I will talk about R trees. But it's also possible that an index can be a primary access too. So there are things called index organized tables. For example, in Postgres, this is called a cluster. So, for example, a cluster in Postgres. Which basically is an index on the top, but at the leaf level, you actually have the data. So basically, you build index in the same way that we have, but at the leaf level, you actually store the data tuples. So you have basically a search structure of an index, plus you store data tuples at leaf levels. No matter almost everything we do, we will talk about this as a model. One of the reasons why this is not as popular is that it takes a lot of effort to maintain these because you have to manually restructure them often. But they do exist, and we will talk about the distinction because that has implications on performance. This can really break and make your system. But we will first talk about this. After you understand this fully, I can tell you a little bit about what happens here. So with that, I will stop, and then on Monday we will do some more B trees. Then I will start giving you a homework. So good.